Greetings. So, we will talk about light atom interactions, and normally when you look at this title, it can be any light, but now with modern sources of light, the main primary sources of light that people talk about is the light that you get from the synchrotron or from the laser. And you do different kinds of studies using either the synchrotron light or the laser light. Some studies can be done by either of these, but some only by one or the other. So we will focus on specific aspects of this. This is a very huge subject. We will be focusing on laser atom interactions to some extent, and obviously the laws of nature being quantum, you need to talk about a quantum of light, which is the photon, and the story to that extent begins with Max Planck in 1899, December 14th, I think. He proposed the quantization of the electromagnetic field to explain the black body radiation, and then in 1905 Einstein explained the photoelectric effect using the quantum of light. But then of course it is the statistical distribution law which was correctly formulated by Satyendranath Bose, which firmly established the statistical distribution which we now recognize as the Bose-Einstein statistical distribution, and particles which obey this or which whose occupation distribution is governed by this are known as bosons. So I like to call H not as just the Planck's constant, but the Planck-Einstein-Bose constant, because I think everybody's contribution, not just Planck's alone, but Planck, Einstein and Bose contributions are important to recognize the quantum of the electromagnetic radiation. So we will discuss this in two segments, not quite independent of each other. They overlap with each other, the physics overlaps with each other to some extent, but then the properties become even more important and interesting as we go from atoms in free space to atoms in cavities. Okay, so we will talk about both atoms in free space, in which the photons come from somewhere, interact with an atom, right? Whereas atoms in cavities are confined to some space, like two reflectors, like two mirrors, all right, and you can inject atoms from one side and a laser beam or optical pumping from the other, right? And then what the reflectors do is they provide some sort of the confinement and feedback mechanism so that the light can interact with the medium which contains these atoms a number of times. So we will talk about atoms in cavities, which brings us to the topic which is generally known as cavity electrodynamics. So we will talk about these things. So let's first talk about the spectrum of an atom in free space, right? And as you see, the bound states are negative. The 0 is when the particle would be just free from the potential, like the nuclear potential in an atom. And the spacing between the energy levels diminishes as you go closer to the 0 of the energy scale. So you begin with some deepest energies and then the spacing in the energies. So typically this is governed in the hydrogen atom by the Rydberg-Bohr law, which goes as 1 over n square, all right? And then you can have resonant transitions, absorption and emission, right, between two levels. no two levels will be separated by the same energy. So, the laser which will have a particular frequency will be resonant with a particular pair of energy levels, and we do this analysis for just this pair of energy levels, all right. And these would be referred to as the ground state and the excited state for this particular interaction. So, you have two states, the ground state and the excited state, and if the atom is originally in an excited state, then it could come down to the ground state not just by one mechanism, but two mechanisms. There is one which is intuitive, the other which is not, which needs Albert Einstein. Okay. So, one is the spontaneous emission and the other is the stimulated emission. The spontaneous emission takes place because the excited state is typically not very sharp. If it were sharp, the atom would not ever get de-excited. Okay. But it has got a certain energy spread, which is the energy uncertainty, and you have an uncertainty relation similar to position and momentum. The analogy is interesting because in the classically conjugate sense, energy and time are classically canonically conjugate variables. Nonetheless, the analogy stops there, because the delta Q delta P uncertainty relation, if you remember, we got it from the spread of the uncertainties in the position and the momentum. So, we defined the operators for the position and the operator for the momentum, and then we worked with the expectation values of the squares of these operators and their differences and so on. So, you remember that whole derivation of the uncertainty, the generalized uncertainty principle. Now, you can't do the same with energy and time, because there is no operator for time in quantum mechanics. Okay. So, the analogy stops there. So, the relationship is similar, the physics is somewhat different. So, nonetheless, an excited state has got a width and therefore it drops. So, there are some models which use part of this idea, but ignore the rest of the idea. Like you include the part of the idea that yes, an excited state would decay, but then you still ignore the fact that it has got a width. All right. So, you consider transitions between sharp energy levels and then take into account the energy levels to have a certain width, and then the relationships actually get modified depending on what you are using. So, you will see that in this class or maybe the next one. So, the rate at which an excited state, which is E2, all right, the excited state denoted by E or the label 2 would decay spontaneously at a certain rate, which will be proportional to the number of atoms present in that particular excited state. So, obviously, the solution would be an exponential solution, because any time you have got a quantity which decays at a rate which is proportional to the amount of that quantity at that point, whether it is decay of charge on a capacitor or whatever, the rate at which water flows out of a beaker if there is an orifice at the bottom. So, you have a relationship which is dN by dt equal to minus is proportional to N2. So, the proportionality is the coefficient which is called as the Einstein A21 coefficient for spontaneous emission, and the solution obviously would be an exponential solution as you have in nuclear decay or whatever, right. It is the same kind of relationship, and you can define radiative lifetime, radiative because a quantum of radiation is emitted during this transition. So, these are Einstein introduced two coefficients A and B, all right, and this was, mind you, in a letter that he wrote to his friend in 1916, he said that a splendid light has dawned on me about the absorption and emission of radiation. And I want you to note that this was in 1916. So, this was before the work of Schrödinger, Heisenberg, and before formal quantum theory. So, the background for this was the Niels Bohr model of the atom in 1913. Okay, so which really belongs to old quantum theory. So, formal quantum theory was not developed at this time, and we are going to use the subsequent developments of quantum theory to interpret this relationship and understand Einstein coefficient. So, we are going to not do this analysis completely in the framework of old quantum theory, but we will be using quantum theory as we know it today to analyze this. But this was a great step on the basis of the Bohr model alone. So, you have this two-state system, all right, and you can have absorption, right, which is induced by the electromagnetic field, and this will require the electromagnetic field. So, there has to be a spectral energy density of photons at that energy to enable this absorption, all right, because the atom can spontaneously decay, but it cannot spontaneously go from the lower state to the excited state. And that is the reason in this rate equation you not only have a proportionality constant B in addition to the number n1, of course, you also have the spectral energy density of the electromagnetic field. Okay? And this field, and this is something which is not very intuitive, but it needs the mind of Albert Einstein. And Einstein introduced that there can also be, if the field can induce transitions from the state E1 to E2, it would also induce transitions from E2 to E1, which will be stimulated emission, right. So, that would again be given by a rate equation which is similar to the other one, proportional to the number of atoms in the excited state N2, the proportionality constant B21, and then it will also depend on the spectral energy density of the electromagnetic field, right. So, this is the rate equation that you get, and now you have these three rate equations, one for the spontaneous emission, another for the stimulated absorption. Absorption is always only stimulated, okay, there can be no spontaneous absorption, and the third is the rate of stimulated emission. And what Einstein proposed is that at equilibrium the absorption rate would be equal to the emission rate, and the absorption rate must be balanced by the emission rate, but the emission rate now has got two components, one is stimulated emission and the other is spontaneous emission, all right. So, there is a minus sign on all the three terms and we can drop those, all right. We can drop those, and now having dropped those, there are two terms with the energy density which we can put together on one side, all right, and then we can factor it out, right. So, we have factored out the spectral energy density of the electromagnetic field and have all the other terms on the other side, and now we can just divide the numerator and the denominator by B21 N2. Every term we divide by B21 N2. So, in the denominator in the second term you have a factor of 1, right, and you have this N2 over N1 which is given by the Maxwell-Boltzmann distribution. Now, this was, I believe, before Bose-Einstein statistics, and it was not a bad approximation. I mean, Maxwell-Boltzmann after all does work in many situations, right. So, he plugged in the Maxwell-Boltzmann term to take care of this N2 over N1 ratio, and in the numerator the N2s of course cancel, and now you have got an expression which is compatible with the Maxwell-Boltzmann distribution for the spectral energy density. Now, this is what you get by considering the rate equations for emission and absorption, and you get an expression for the spectral energy density. However, what was also known at that time was Planck's formula, right, which also gives this, and Planck had come up with an expression which involved the quantum of energy, and Planck's distribution law is what you see here in this blue, and these two relations that you have got for the spectral energy density must be exactly equal. Okay? So, they have to be compatible with each other. You cannot get a different relation from one formula and another from the interpretation of the black body radiation. And now, if you look at the right hand sides of these two and ask yourself, under what condition would the right hand sides be the same, then you immediately recognize that two conditions must be satisfied, that the ratio A21 to B21 would have this omega cube other than the remaining constants, and second, the B12 and the B21, which are the proportionalities involved in the stimulated absorption and the stimulated emission, they must be equal except for the degeneracy factor G, right. So, if the degeneracy factors were the same, G1 and G2 were the same, then B12 would necessarily have to be equal to B21, right. So, this is something which we know subsequently from quantum mechanics, quantum theory as was developed later, but this was based on primary consideration of balancing the emission and absorption rates. So, you have this relationship, and you have the corresponding lifetimes for different kinds of processes, and if you consider transitions which we call as the electric dipole transitions or the quadrupole transitions, you have different lifetimes. These are typical lifetimes. You can also have a magnetic dipole transition, and they have different lifetimes. Okay, so we will now talk about these transitions in the two-level systems, and now we use formal quantum theory. So, focus on the two-level system, and the general state would be a superposition of state 0 and state 1, right. So, you consider the state 0 and 1 to be denoted. Here is an example of nuclear or electron spin, and these two states would be essentially degenerate, but in the presence of a magnetic field due to the Zeeman interaction, which we have discussed earlier in our previous discussions, they would get split, right. And this is an example of a two-level system, and the general state would be a superposition of the state 0 and the state 1. So, it would be like an entangled state, as we have discussed in the quantum in the context of quantum entanglement. So, this is a superposition of states 0 and 1. The coefficients give you the probability amplitudes that the system would be found in one or the other, and their modular squares will give you the corresponding probabilities. Now, you have to remember that this is different from a mixture of state 0 and state 1. You can certainly construct a mixture of these two states in such proportions. So, if Nt is the total number of atoms which are available, and n0 of them are in the state 0 and n1 in the state 1, right, then their ratios can be chosen to be in the same proportion as alpha 0 square and alpha 1 square. So, there is a certain similarity between these two, but they are completely different kinds of systems, because one is a quantum superposition of 0 and 1, the other is a classical mixture of the states 0 and 1. So, there will be no interference that will be seen in the classical mixture, whereas you have you will witness the quantum interference in what is a superposition of the state 0 and 1. So, that is the coherent superposition, and this coherence is a quantum property which really brings about very fascinating results. So, it will impact the density matrix. For example, if you express the density operator in the basis of coherent or incoherent basis, then the density matrix will not be diagonal in the coherent superposition states, whereas it will be, because there is no interference between the two states. So, this is the general picture that we are looking at. You have got absorption at the rate B1 you have got emission, spontaneous emission, which is the rate A21, and then you have got the stimulated emission, in which you have got 1 photon in and 2 photons out, right. And let us consider a system. You have two states which were denoted by 1 and 2, and now you have got this atomic system which is interacting with the electromagnetic radiation. So, that interaction we will represent by an operator, which is the operator V, which is time dependent, because the electromagnetic field is time dependent, right. So, you have got a laser atom interaction, and the energy of the photon may be tuned exactly to the energy difference between the two levels, which will be sharply resonant, or else omega may be slightly different from omega 0 by a difference delta omega, right. But we will consider those cases when delta omega is very small, so that the interaction is at an energy of the electromagnetic field which is very close to the resonant energy difference between the two states. So, each individual state psi 1 and psi 2 is time dependent, and this time dependence is governed by the dynamic phase, which is e to the minus I E over h cross t as we know it, right. So, these are the stationary states solutions to the problem, and the unperturbed problem of H0 has got eigenstates which belong to the eigenstates of the time independent Schrodinger equation. The time dependence is given by the phase e to the minus I E I over h cross t, right. But the general Schrodinger equation for this system is h psi equal to I h cross del psi by del t, where the psi, the wave function, is now a superposition of the basis states psi 1 and psi 2. It will have time dependence which is coming from the dynamic phase of the independent states, but also the coefficients will be time dependent because the interaction is time dependent. All right. So, the time dependence is factored into these two terms. One is the stationary state dynamic phase, and the other is the time dependence of the coefficient itself. So, this is the Schrodinger equation, and the rest of there is a little bit of discussion we should work out, which is formal manipulation of these terms, which is something which a high school student can do quite easily. So, I will not spend much time on that, but I will take you quickly through these steps. So, essentially you have this Schrodinger equation, and if you look at these terms, on the left hand side you have got two terms, all right. you need to write them out carefully. On the right hand side, you have to take the time derivative of the two terms on the right side, right. But you have to take time derivative, and each term has got two functions of time, one coming from the phase, the dynamic phase of the stationary states, and the other time dependence is coming from the time dependence of the coefficients. So, you are taking the partial derivative with respect to time of a product of two functions. So, it will be one function times the derivative of the second plus the derivative of the first times the second, right. So, you have to take into account this carefully, take the derivatives of the two terms and now write them out carefully, right. And then recognize that there will be some common terms on the left side and the right side, right, which you can happily cancel. Okay. So, that this is a straightforward algebra that you can work out quite easily. And having cancelled the common terms, what you are left with is a more compact relationship. And let us analyze this, because we can take the projection of this on the state psi 1, which is to construct this inner product, and then exploit the orthogonality between the states psi 1 and psi 2. Okay. So, when you take the projection on psi 1 of this relation, the term involving the integral psi 1 psi 2 will disappear, because psi 1 is orthogonal to psi 2, right. And the other term will give you the matrix element of the interaction operator V in the states which are involved. So, once you write it down, you get the expression for the time dependence of the coefficient C1, and a similar relation you get by projecting that equation on psi 2 for the time dependence of C2. So, now let us look at these two relations. Okay. Out of these, we will consider the dipole interactions. Okay. We have discussed the dipole interaction in our earlier discussions. Basically, you can have a dipole transition only between states of different parity, because the dipole operator itself will change its sign under inversion. So, what does it mean? It means that V11 and V22 would be 0. Okay, there will be no transition from S to S, for example, or P to P. You have a dipole transition from S to P and P to S, but not S to S and P to P orbitals. Okay. So, V11 and V22 would be 0. So, now you drop those terms, recognize the form of the interaction operator. On the cosine term, you write in terms of the exponential terms, exponential functions. So, now it gives you an expression for the matrix element Vij, I and j both being 1 and 2, but then V11 is 0, V22 is 0. So, you have only V12 and V21 to work with, and they will then extract the common terms, which are exponential functions, and then you have got the matrix element, which is the matrix element called as the dipole matrix element, which I have denoted here with Dij. Okay. So, the operator itself has an odd parity. So, D11 is 0 and D22 is 0, as I mentioned earlier. So, here we have consolidated these results. So, for C1 dot and you have got a similar relationship for C2 dot. Okay. They are very similar to each other, and what we can do is recognize the fact that the dipole matrix element would be real okay. So that D21 and D12 would be complex conjugate, but being real they will be equal to each other. So both will be denoted as D12, okay. And you have this factor of I over here, which you can take to the numerator when it becomes minus I, and this minus sign with this minus will give you a plus I in the numerator, and then you have got this 2 and h cross in the denominator. So this is just a manipulation of these terms to rewrite it in somewhat simple manner, which makes it easy to analyze. And now what we do is to rewrite this in terms of a new factor, which is epsilon 0 times d divided by h cross. This has got the dimensions of frequency, okay, and this is called as a Rabi frequency. So this factor epsilon 0 d over h cross, so this is now replaced by omega r, which is the Rabi frequency. So it is the same equations which have been written here, except that we have now introduced what is called as the Rabi frequency. And we have to ask if this is going to be the same as the resonant frequency. Is it different? Are there other factors to consider when we talk about the Rabi frequency? We will also introduce what is called as the generalized Rabi frequency. So we have to be alert to the details of this particular term. So it's going to play a very important role in our analysis. And now we are going to look for the solutions of these two equations. So you have got two differential equations. They are obviously coupled differential equations, right? And because C2 appears in the time dependence of C1 and C1 appears in the time dependence of C2. So you have coupled differential equations, and we will seek solutions in two different limits, the weak field limit and the strong field limit. In the weak field limit, if you have the atom originally in the state 1, which is the lower state E1, right, and the field being weak, you will not have too many atoms which go to the excited state, all right. So you can consider initial states to be C1 at t equal to 0, which is the initial state t equal to 0, to be equal to 1, and C2 to be equal to 0. So that's a good approximation for the weak field. Now in the weak field limit, we have to solve these coupled differential equations. We have not considered the width of the levels as yet, okay. So just keep that at the back of your mind. And you now have with the initial conditions C1 equal to 1 and C2 equal to 0, the C2 dot will be given by this. C2 dot is the time derivative of C2. So you solve for this differential equation subject to initial conditions. So what do you have to do? You just have to integrate this differential equation. So once you integrate it, you will get a constant of integration, right? You will have terms in omega plus omega 0 in the denominator, and also omega minus omega 0 in the denominator, okay, out of which you have to use this to determine the constant of integration, because you know the initial conditions. So once you put the initial conditions, then you find what the constant of integration k is like, and then rewrite the solution with the constant of integration, and now you have this relationship here in which the constant of integration has been determined with the use of the initial condition, right. And this is what you get for the coefficient in the state 2, which means that its modulus square will give you the probability of transition. So you are getting a measure of how likely the atom is to undergo transition from the ground state to the excited state. And once you get this probability, if you can find the rate of this transition probability, you will then be able to connect it with the Einstein coefficients, right. So, that is the idea that we are following. So, we now make an approximation which is called as a rotating wave approximation, RWA. We will introduce it more formally a little bit later, but for the time being I might remind you of the fact that we have in a certain sense already used this in our discussion when we talked about transitions between two state systems, when we talked about qubits in our previous unit on Introduction to Quantum Computing. So, you had an oscillatory field in a spin half system which was placed in a magnetic field, and to induce transitions between the excited state and the ground state, we introduced a transverse oscillatory field which we could resolve in a circularly polarized, a right circularly polarized and a left circularly polarized. So, that is the picture I am reminding you of by these blue and the red circles. So, you have got a linearly polarized field, and then in the rotating frame of 1, okay, you will have the magnetic moment's orientation to be constant, but if you pick it to be the red one which is going like clockwise rotary, and the other which is anti-clockwise rotary, would then be moving at twice the frequency in the opposite direction, right. So, twice the frequency makes it move well away from the resonant frequency, and it is not going to interact with the system very much, okay. So, which is why the omega plus omega 0 term, okay, is not going to contribute very much to this interaction. So, if you look at these two terms that you have in the solution, you have omega plus omega 0 in the bottom and omega minus omega 0 also in the denominator, right. So, omega plus omega 0 will be much larger, whereas omega minus omega 0 is a small one. The numerators are of the same order of magnitude. You have got an exponential function which is a sum of cosine and sine terms, and no matter what its value is at a given instant of time, it will always be between minus 1 and plus 1, right. So, the numerators are of the same order of magnitude, but the denominators are different. One is tiny, the other is large. So, it is quite understandable that you can ignore the term in omega plus omega 0 because that will not contribute very much to this interaction process. So, this is called as a rotating wave approximation, and in the rotating wave approximation then you ignore that term, and the remaining term, after you take care of the minus sign, you cancel this I with this I over here, but then there is a minus sign here. So, instead of this term minus 1, you get 1 minus the other in the numerator, all right. So, this is your solution for C2T, which is the probability amplitude that the atom would be found in the state 2 at the time t, and its modulus square will give you the probability of this transition. So, the modulus square is the product of C2 with its complex conjugate, right. So, you work out this product of these two terms, one is the complex conjugate of the other, multiply it out, you get a term which is 1 minus cosine of omega minus omega 0, which you can write in terms of the sine square of omega tilde t by 2, omega tilde being the difference in the two frequencies, okay. So, I have used the symbol omega tilde over here, later I might use the term delta over here, but basically this is the difference frequency. This is like the detuning term. Okay? So, if omega is exactly equal to omega 0, at exact resonance omega tilde would be 0 and the field would be completely tuned to the resonant transitions, but otherwise this omega tilde, this difference omega minus omega 0 is a measure of this detuning. So, now you get this term in which you have got sine square over this omega tilde in the denominator and the whole thing is squared. So, you have to handle this term carefully, because if you let this delta omega go to 0, then you will find that in this limit the modulus square goes as t square. Now, this is strange. This is really strange, because what you are getting is that the probability is going quadratically with t, right, t square, and this is obviously wrong, because when we discuss time dependent perturbation theory, and I have it in some other NPTEL lectures which you can look up, where we have used the Fermi golden rule to determine the transition probability from a ground state to the initial state. We find that this expression cannot go as t square, but it has to have a linear dependence. And the reason we got it wrong is because we ignored the width of the upper level. Okay? So, when we factor that in, we will get the right result, which we will work out now. All right? So, this width has to be taken into account, and when we do that, we will get a result which will be in agreement with the Fermi's golden rule, but that is for the next class. So, again I want to remind you that we sort of mix a few ideas. All right? We do take into account the width of the level, but not doing so does not prevent us from thinking about a spontaneous emission. Okay? Strictly speaking, if the upper level had infinitesimal or zero width, if it was exactly sharp, then an atom in an excited state would stay there forever and ever and ever and ever. Okay? But it does decay spontaneously, and the reason it decays is because there is a width. All right? And there is this energy time uncertainty. Then again we have to remind ourselves that yes, there is energy time uncertainty, but there is no operator for time. And this actually comes from the fact that the atom can actually interact with the rest of the universe. So, when you have solved the Schrodinger equation and you get the bound states, you have solved the problem only for the atom, pretending that it is a completely isolated system. You have ignored its interaction with the universe. So, it is like ignoring the hidden degrees of freedom when we are dealing with friction. So, there are decay mechanisms, so that energy can be transferred to other degrees of freedom, which you have not taken into account in your equation of motion. So, that is the reason you do not get this width when you solve the Schrodinger equation for the hydrogen atom. You get sharp levels. It goes as 1 over n square, you get a number and just a number, not that number plus or minus something, right? So, we will have to consider this energy distribution, and the energy distribution means you can see on the lower right. So, if you integrate the spectral density distribution over a certain frequency range, you will get the corresponding energy, right, rather than something being very sharp. So, I will stop here. I can take a few questions, otherwise we will proceed from here in the next class.
When we always talk about decay, why we directly consider it to be directly proportional and not something else? I mean, like something like proportional to the n square or under root of n or something like that. Why always directly proportional to the quantity present?
When we talk about decay,
any kind of decay.
Yeah, any kind of decay. in principle means you can think of other relationships, but then here the way nature operates is that even in populations, for example, if populations grow, the growth rate will be proportional to how many persons there are. Okay, there may be other mechanisms, there may be coronavirus, and so you have to consider some feedback mechanism and correct that, right? But if you are not taking into consideration these feedback mechanisms which will control the population, it will grow at an exponential rate. Similarly, if you have charge on a capacitor, and then the charge does not stay on the plates, but you have a circuit, and then the charge is going to come down because the charge is going to begin to flow in the circuit, then the rate at which it will go will depend on how much charge there is. And this is an amazing contribution of Euler, who recognized that in the natural phenomena there is, so this is the natural Euler function which is involved over here, right, this exponential function. So this is characteristic of natural processes. And the change in population in most situations, if you did not take into account any feedback mechanism like death or loss due to anything else, then it will be an exponential function. And that, if you carry out either the inverse differentiation or integration, you immediately see that you have the rate dN by dt, which will be proportional to the amount which is present, because the rates are governed by an exponential law. So the exponential law is very intrinsic to many natural processes. It's a fascinating function. Its differential is the same, its integral is the same, right? And that is what makes it unique. And that's the reason you always consider the rates to be proportional to the amount which is present. It's because of the predominance of exponential functions in nature. Any other question?
Sir, because we are assuming here the second level is little broad, that is why when we observe the emission spectra of any atom, that is why it also contributes for the broadening of that spectrum.
Yeah, it is one of the factors which is involved in the broadening of the spectrum. There may be other sources of broadening, like because of motion and Doppler broadening and so on. But certainly this is one of the factors.
And another one, sir, why
this
we
is,
are not...
this is what is called as the natural width of the line.
Sir, why we are not considering E1 also, E1 plus delta E by 2, only the upper level to be little...
The ground state is sharp. The ground state is sharp, it has got infinite lifetime. Spontaneously it is not going to decay. Okay? So if the lifetime is infinite, the energy width becomes 0. So the ground state is sharp. You are considering just a 2-level system. So out of which the ground state will have infinite life. Spontaneously. You can pump it. That's where the Einstein B coefficient comes in. Any other question? Otherwise, we'll take a break here. Thank you.